Hello and welcome to our lesson on finding the area between two curves. So basically the concept we're looking at here is the same as the concept we talked about in the previous topic, where we're trying to find the area that's bounded by two vertical lines, and in the previous topic it was a curve and the x-axis. So we're looking between some function and the x-axis, and then on a closed interval we had these vertical boundaries. It's the same concept here, except instead of the x-axis having to be one of our boundaries, that second boundary, it could still be the x-axis, but it could be some other function. Okay, so we're still going to be finding an area that's bounded, which means it should make sense that we're still going to be evaluating a definite integral to find that area. So if f and g are continuous functions, that's a typo, didn't see that one till now, continuous functions on the closed interval a to b, and f of x is greater than or equal to g of x for all x in the interval, I'll show you what that means in a second, then the area that is bounded by their graphs and the lines x equals a and x equals b, those are just our vertical boundaries, the closed interval, then the definite integral is going to get us the area that we're looking for. And that definite integral is going to be of the difference of our two functions. Okay, so let me show you the picture of what I tried to say there, and I probably butchered because I was a little distracted by my typo. Okay, so we've got two continuous functions. So let's say that this is f, or f of x, and then let's say we have this second function over here. I'm just going to call this one g of x. Okay, what we have is f of x greater than or equal to g of x for all x in the interval that we're looking at. And let's say we're looking at this interval that starts at a and then stops at b. So here's our vertical boundary at a, here's our vertical boundary at b. And now the other two boundaries, again, it's not the function or some function in the x-axis, it's two different functions creating this area here. So this would be the area that we're going to try to calculate using a definite integral. Now, the rule here is that when we're integrating, it's calculating a definite integral or evaluating a definite integral just like we did before, but the integral will be of the upper bound minus the lower bound. That is the higher function, the greater function, minus the lower function. So here it is. Again, the area that we're looking for, which is that highlighted bounded area, is going to be found by evaluating the definite integral that starts at a, ends at b, of the difference of our two functions, where the greater function is first minus the lesser function is going to be next. And then that's it. So we're still calculating, making the same calculations we were doing before. There's just one additional step here. We're going to subtract two functions before we integrate, but then we'll evaluate the same way we did. So just once again, this is going to be called the upper bound, and it should be the higher of your functions, the greater or higher of the functions. And then this is going to be the lower bound, so the lesser or lower of the two functions, or the lower or upper graphs. Okay, those actual boundaries. Which one is upper, higher, goes first. Which one is lower, goes next. Okay, so let's look at an example, and hopefully this work will feel familiar. So number one, we're trying to find the area that's bounded by y equals x squared plus 2 and y equals x over the closed interval from 0 to 1. So there's just one extra step from what we were doing before, and that is to subtract our two functions. So in order to do this correctly, we have to know which function is the upper bound and which one's the lower bound. Now I already know because I'm very comfortable with knowing what these functions look like. If you wanted to produce these graphs in Desmos, you absolutely could. I'm also hoping that you have a pretty good handle on what these graphs are going to look like. So I'm going to go ahead and sketch this out without having to use my technology. I know that this is my parent quadratic function that's shifted up to. So I'm just going to sketch this one out, shifted up to quadratic parabola, looks like that. And I know this is my parent linear function, so that's a diagonal through the origin, so that's going to look like this. And here we are looking at the closed interval from 0 to 1. So from 0 to 1, that would be this little area These are our vertical boundaries here from 0 to 1. So the area we're trying to find is this space in here that's bounded by those two vertical boundaries and those two graphs. So according to our formula, this area, put this up here, this area is going to be equal to the integral that starts at 0 and stops at 1 of the upper bound minus the lower bound. So in this case, the upper bound is f of x, that's higher, that's greater, and the lower bound, g of x here is going to be x, so the quadratic is going to go first, the linear is going to go second in this difference. So it's, I gotta sneeze. Excuse me. It's going to be x squared plus 2 minus x, and we differentiated with respect to x. Okay, now I use parentheses to separate those two functions because it's good practice. It doesn't really affect this problem here, but please be careful with this. If you are subtracting a function that has more than one term, we need to make sure that negative gets distributed to all the terms that follow. Okay, so using parentheses, again, good practice. So we're really trying to find the definite integral from 0 to 1 of, we're going to have an x squared, a negative x, and a positive 2, and this will be pretty easy to integrate. So we're going to be left with x cubed, just using our power rule 3 times here, divided by 3, minus, we're going to have an x squared divided by 2, plus we're going to have a 2x. Now I know there's a plus c here. I'm going to leave it off because I know it's going to cancel when I go to evaluate this antiderivative. But if you don't want to forget it later on when you're doing the indefinites, then you can definitely put c there. But this needs to be evaluated at 1 and again at 0, and then we're going to subtract those two results. So this is the same work we were doing before. So first I'm going to plug in the 1. That's going to be 1 cubed over 3, 1 squared over 3, and 2 times 1. And then from that we're going to subtract, well, if we plug in a 0, everything is going to 0 out, but just for thoroughness, I'll go ahead and write all this out for you. Okay, so that whole thing zeroes out, so we really just need to focus on what we have here. So 1/3 minus 1/2 plus 2, and I'm going to try to do this without a calculator. Common denominator is 6, so multiplying by 2 over 2, I get 2 over 6. Multiplying by 3 over 3, I get 3 over 6. Multiplying by 6 over 6, I get 12 over 6. So 2 minus 3 is -1. -1 and 12 is 11. So our area is 11/6 units squared. Square units. That is our area. And we've done it. So again, almost all the same thing we were doing in our previous topic with just one additional step up front. And to do this additional step, we have to make sure we know which function is our upper bound, which one is our lower bound, and then we're good to go. Alright, so let's just practice this a few more times. Notice on example 2, our functions are almost the same. We have a quadratic, we have the same linear, almost the same quadratic as well. We're still finding a bounded area, but we aren't given a closed interval. And you're going to see why in just a second. So again, I'm going to start by sketching this out. And I don't need technology for this. If you do, that's totally fine, but again, I know what these graphs look like. So this is my parabola. It's going to be upside down and shifted up 2. So shifted up 2 and upside down. That was pretty terrible. Going to look something like this. A little more symmetric than I drew it, but that's okay. And then this, my parent linear function. Okay, now I need to draw this a little bit better. Oh no. Don't mind me. Goodness gracious. Okay, whatever. Something like this. I'm getting a little too picky with my work here. Parent linear function diagonal through the origin, so that one's going to look like this. Now you see when we put these two graphs together, I don't need a closed interval because the interval closes itself. There is already an area bounded by these two functions. There is already a set area between these, and it happens here. This is the area between the two curves, right? Already on a closed interval. So I know when I go to find this area, it's going to be a definite integral. One small problem, I can see the closed interval, but I don't specifically know what the x values are that belong in this definite integral. So again, I could put this in Desmos and easily find those points, but you should be pretty comfortable with the algebra. What I need to find is where my parabola is equal to my line. That's where those two intersections are. So I'm going to make these two equal, do a little bit of algebra here. Where is 2 minus x squared equal to x? I'm going to add these two terms over. So I'm looking at 0 equal to a positive x squared, a positive x, and a negative 2. This factors into x plus 2 and x minus 1. So x equals negative 2 and x equals positive 1. Those are my vertical boundaries here. So that's where x is negative 2 and that's where x is positive 1. So this is going to go from negative 2 to positive 1. And again, calculator could have given you those, but you should be comfortable with that algebra as well. So our upper bound, again, happens to be our quadratic. Our lower bound, again, happens to be our linear function. So here I want to subtract. It's going to be 2 minus x squared minus x. And after that subtraction, I can integrate and evaluate and be done. So this is the integral, again, from negative 2 to 1 of a negative x squared, a negative x, and a positive 2. Almost the same thing that we just did. So we're looking at a negative x cubed divided by 3 minus x squared divided by 2 plus 2x. Again, let's evaluate this thing at the upper limit of 1 and the lower limit of negative 2, subtract those results, and then we will have our area. So let's evaluate at 1. Maybe we can skip some of the work here. Negative 1 cubed is going to be, well, 1 cubed is 1, but times a negative makes it a negative 1. So it's going to be a negative 1/3. Put this negative 1/3. And then if I plug 1 into this, I'm going to get a 1/2, and it's going to be negative. And then if I plug into this, I'm going to get 2. And then from that, I'm going to subtract, let's see, the result of plugging in a negative 2. So negative 2 cubed is negative 8. Times a negative is going to make it a positive 8. So I'm going to have 8/3. And then negative 2 squared is 4, but it becomes a negative there, so this will be minus 4 over 2, and I know that's 2, but that's fine. And then plug in here, and I get a negative 4. And now let me distribute that negative. And I'm going to get common denominators at the same time, which again, my common denominator will be 6. So this is going to be a negative 2 over 6, a negative 3 over 6, a positive 12 over 6, a negative, when I distribute here, 16 over 6, a positive 12 over 6, and then a positive 24 over 6. And now it's some adding and subtracting, and I'm good. So negative 2 and negative 3 is negative 5. Negative 5 and 12 is going to be 7. 7 minus 16 is negative 9. Negative 9 and 12 is 3. 3 and 24 is 27. So I have 27 over 6, and that reduces. 3 goes into both of those. We get 9 halves. Square units, units squared, that is the area that we have bounded by those two curves. Boom. Okay, so hopefully you're picking up what I'm putting down, and this again feels familiar, very similar to the previous topic. We're just going to look at a couple more just to make sure we're prepared, and then we'll be good to go. So this time we're finding the area bounded by another quadratic and the x-axis, so almost the same thing we were doing before, but again we don't have a closed interval. That's okay, you're going to see it close itself. So if you want to use technology, again, to do this, you could. To graph, you could. I'm not going to because, again, I think the algebra is good for you to know. So let's look here. If I wanted to sketch this parabola, it's not in our transformational form. I do know that it opens upward because we have a positive leading coefficient, and I can easily find where it's going to cross the x-axis because this thing factors. It factors into an x minus 4 and an x plus 1, and if again I can make zeros there, I'll know where it crosses the x-axis. So at x equals 4 and x equals negative 1, I'm going to have 1, 2, 3, 4. I'm going to have 2 x-intercepts there. Oops. So I'm going to graph this first one here, crossing the x-axis at negative 1, positive 4, and then somewhere up here, oops, drew it the wrong way. Somewhere down here it's going to have a turning point. I'm not really concerned with where that is just yet. If I need to find it, I will, but we're looking for the area that's bounded by that parabola and the x-axis. So the x-axis, which I'll do this one in red. Obviously we know where the x-axis is, but the equation here for the x-axis, that's where our y is equal to 0, and we're going to kind of need that when we put in f of x minus g of x right into our integral. So the area that's bounded by the x-axis and that parabola, this is the area that we're looking for. And really easy to set this up now because I know that this x value is -1. I know that this x value is +4. So our area is going to be the definite integral that starts at -1, stops at +4, and it's going to be f of x minus g of x. This time the upper bound is actually the x-axis, so that's going to be 0. And from that we want to subtract the lower bound, which is x squared minus 3x minus 4. And again, this is where it's really important to make sure that you have parentheses to distribute the negative to all of that. So we have to make sure we subtract that entire function. So we're going to try to integrate from -1 to 4 a negative x squared, positive 3x, and positive 4. Again, that's just using our power rule a few times. So we have a negative x cubed divided by 3 plus 3x squared divided by 2, and then plus 4x. Again, I'm going to leave c out of the picture here. If you want to put it in, you can, but this needs to be evaluated at 4, and again at -1, and then we're going to subtract those results, and we will have our area. I'm doing good on space here, so I'm going to keep going this way. So let me plug the 4 in. 4 cubed is going to be 64, so -64 over 3. And then 4 squared is 16. 16 times 3 is 48, so that's going to be 48 over 2. And then 4 times 4 is 16. So that's what we get when we plug in the 4, minus, let's plug in the -1. So a -1 cubed is -1, but times a negative will make it positive, so we get a 1/3 there. -1 squared is 1, times 3 is 3, so that's going to be 3 halves there, and then a -4 for that last product. Alright, common denominators, again, going to be 6. And I'm not going to lie, my brain is wearing, so I'm just going to go ahead and throw this in the calculator, because I don't want to. I just don't want to. And my luck, my brain will be running out. Okay, so from this I want to subtract 1/3. Be a real shame if I'm already messed something up in what I'm putting in the calculators wrong, but I'm going to hope I'm okay. So it gives me this decimal answer, and I don't want this decimal answer because it isn't precise. If you had a terminating decimal, by all means use it, but if it's not and you can convert it to a fraction, that's going to be the preferred answer. So we're going to go with that one. It is 125 over 6 square units for this area. Okay, we've done it. Alright, so one last one, basically the same thing. The area bounded by these two curves. We aren't given a closed interval, which just means these two graphs are going to intersect. And I already know which one, I think I know which one's going to be the upper bound, because this parabola is upside down. Actually, we might have two areas in here, but I put one more example in here for a couple of reasons. Something different is going to happen on this one, but also I want to show you how you can just use Desmos to get your picture. So let's do it. Let's let Desmos do the heavy lifting on this one. Let's go ahead and graph 3x to the 3rd power minus x squared. And you could do the same work we did on the previous, find the x-intercepts and sketch this out, but you would have to know n behaviors of a cubic function to do that, which is fine. I mean, technically you should know it. Alright, so here's this graph, and we want to know the area that's bounded by that, and looks like we're going to have two areas here. A negative x squared plus 2x. Oops. Plus 2x. Nope. Fat fingers. Okay, yeah, we do have two separate areas here. Let me see if I can't get this so I can manipulate it a little bit in my document. Don't mind me. And let me get rid of that. That looks good. Done. Copy and delete. And allow it to paste. Boom. Okay, so now I don't need this. Okay, so we got the graph from Desmos. Thank you, Desmos. The blue one, that's our cubic. And the green one, that is our quadratic. So if I'm looking for the area that's bounded by these two curves, I actually have two different areas. So I have this area here, where the cubic function is the upper bound and the quadratic function is the lower bound. And then I have this separate area over here where the quadratic function is the upper bound and the cubic function is the lower bound. So if I want to find the area that's bounded by these two functions, I actually have to find two separate areas and add them together. So here, my area is going to equal, I'm going to do this. Let me coordinate the colors here. I should have used something that I have a color for. Yeah, this will work. Pink and green, because I have pink and green pens. Okay, so first I'm going to do this area, and then second, why did I number that over there? I meant to do this. I'm going to do this area. I'm going to just call this area number 1, and I'm going to call this area number 2. Okay, so it's going to be area 1 added to area 2. So I have to do both of those. Okay, so the first one, the first area, is going to go from, well, I still have it in here. This coordinate, I kind of need that, is at -2, -8. I need that because I need to know that boundary. And then this coordinate here, obviously that's the origin. And then this coordinate here, that's not too hard to see. That's going to be at +2, 0. It's another benefit of Desmos, because it shows us all the information that we need. Okay, so this first integral is going to go from x equals -2 to x equals 0. Those are the endpoints of that region. So we're going to go from -2 to 0. And that's f of x minus g of x. The upper bound is the cubic, so 3x cubed minus x squared minus 10x. And then we're going to subtract the lower bound is the quadratic, so subtract a -x squared plus 2x. And then we're going to add to that, in pink, number 2 here. And this one goes from 0 to 2. So from 0, oops, still a highlighter. From 0 to 2, f of x minus g of x. So in the second region, again, the quadratic is the upper bound. So -x squared plus 2x minus the cubic is the lower bound. And okay, so now we have it all set up. Let's go ahead and subtract the functions and then evaluate those integrate and then evaluate the antiderivatives. So the first one we're looking at, let's see, it's going to be, let me do a little bit of side work over here. If I distribute this negative, it's going to be a +x squared and a -2x, and so I'm going to combine like terms. I'm going to have a 3x cubed, +x squared, -x squared are going to cancel, and -10x and -2x make a -12x. And that's from -2 to 0. And then I need to add onto that the pink one, which is from 0 to 2. So again, distributing, that's a -3x cubed, a +x squared, and a +10x. So it'll be a back to pink, a -3x cubed. Again, the x squareds are going to cancel. +2 and +10 makes +12x. All right, one step closer. So we're looking at the integral here is going to be 3x to the 4th divided by 4 minus 12x squared divided by 2. Again, I'm going to skip c, and this has to be evaluated at 0 and at -2, plus the second one. We have a -3x to the 4th divided by 4 plus 12x squared divided by 2. And then this one we're going to evaluate from 0 to 2. Okay, almost there. just the arithmetic part now. So plugging in a 0, that's easy. We're going to end up with 0 for both of those terms. Then I need to subtract what I get when I plug in the -2. So -2 to the 4th is going to be 16, times 3 is 48, and 48 divided by 4 is actually 12. So there's the first one. Plus, over here, when I plug in 2, 16 times the -3 is -48. -48 divided by 4 makes a -12. And then plug in a 2 here. 2 squared is 4. 4 times 12 is 48, divided by 2 is 24. So positive 24. And then from that, I want to subtract, I plug it in a 0, so that's going to be 0 again. So I have a -12. And then over here, -12. Uh-oh. What did I do? I definitely don't think I'm getting a 0. 2, 16, -48, -12. Okay, I feel like I goofed up something. Oh no, wait, yeah, something. Something is amiss. Let me do this again. So I think I'm good to here. My arithmetic, it's the brain's falling apart. You're probably thinking the same thing, like why? Okay, so if I plug in a 0, everything zeroes out, that's good. Minus, when I plug in the -2, I'm going to get 48 divided by 4 here. So let me just, not trusting my brain now. So 3 times -2 to the 4th, all divided by 4 is 12. And then plug in, let's see, 12, -2 squared divided by 2 is 24. And I need to subtract that. Did I forget that? I sure did. I think I forgot to do the second. You're probably like, what is she stupid? Okay. And then over here, plugging in the +2, this is almost the same. So this should be negative, and this will be positive. So that's going to be a -12. And then this will be 24. And then when I plug in the zeros. Okay, so I forgot this piece last time. My apologies for that. So this is going to be -12 here, but times the negative makes it a +12. And then over here I have a +12. So 12 and 12 is 24, and that sounds good. So 24 units squared, that is the area here. And we did it. Okay, so obviously lots of little places to make mistakes. Maybe you don't want to go as quickly as I tried to on this, and maybe you want to rely a little bit more on the calculator. I'm totally okay with that, especially for that arithmetic. That's not what we're testing at this level. But hopefully the concept feels okay. You're just evaluating definite integrals. Just be really careful with those signs, and as you can see, the arithmetic. Okay, so you should be good to go for your homework, but as always, if you have questions, you need some extra help, then just reach out. Until next time, take care.